Identify the molecular geometry and polarity of both molecules. Both carbon tetrachloride, CCl4, and carbon tetraiodide, Ci4, consist of a central carbon atom covalently bonded to 4 halogen atoms. Based on VSEPR theory, both molecules possess a highly symmetrical tetrahedral geometry. Because of this perfect tetrahedral symmetry, the individual polar covalent bond dipoles, C, Cl, and Ci, pull symmetrically in opposite directions and completely cancel each other out. Therefore, both CCl4 and Ci4 are nonpolar molecules with a net dipole moment of exactly 0. Identify the primary intermolecular forces, IMFs, at play. Since both substances are nonpolar, they cannot undergo permanent dipole-dipole attractions or hydrogen bonding. Instead, the only intermolecular forces holding the molecules together in their condensed phases, liquid and solid, are London dispersion forces, LDFs. Compare the factors that influence London dispersion forces. London dispersion forces arise from temporary, instantaneous dipoles created by the movement of electrons within a molecule's electron cloud. The strength of these temporary dipoles depends directly on the polarizability of the electron cloud, which is the ease with which the cloud can be distorted. Polarizability increases significantly with an increase in the size and total number of electrons in the electron cloud. Compare the electron clouds of CCl4 and Ci4. Iodine, I, is located much lower down group 17 on the periodic table than chlorine, Cl, and possesses a much larger atomic radius and many more shell electrons. Consequently, the Ci4 molecule has a significantly larger and more polarizable electron cloud compared to the smaller CCl4 molecule. Relate IMF strength to the physical states observed at 25 degrees Celsius. Because Ci4 has a much more polarizable electron cloud, its London dispersion forces are dramatically stronger than those in CCl4. At 25 degrees Celsius, the ambient thermal kinetic energy is high enough to overcome the weaker dispersion forces holding CCl4 molecules together, allowing it to flow as a liquid. However, this same thermal energy is insufficient to overcome the much stronger dispersion forces in Ci4, keeping its molecules tightly locked in a structured lattice as a stable crystalline solid. This confirms option D is the correct answer. The correct answer is option D. The London dispersion forces are stronger in Ci4 than in CCl4 because Ci4 has a more polarizable electron cloud than CCl4.